Okay, so far we studied deflection in the axial direction. So if I plot, see if I can plot, yes. If I consider a beam that had some axial load like N, we discussed this, that it is going to have some deflection like that. This is delta over 2, symmetrically loaded from two sides, and we computed the deflection according to the Hooke's law. So if I want to write it down here, it's simple. Sigma is equal to E epsilon N over A is equal to E delta over L, and L is simply its initial length, L0, before the deformation. And that's going to give me an expression for delta is equal to NL over EA. And we mentioned that the sole purpose of doing this kind of deflection analysis in this course is to be able to get additional equations so we can handle the indeterminate problem or a statically indeterminate problem. There was another kind of loading. So this loading kind 1. There was another kind of loading that it was torsion. So if we have a shaft that has some kind of torque, M here, the opposite here, this is going to deflect, and the deflection here is angular phi. And we actually found the expression for phi in terms of the given specimen length, the torque, and shear module of elasticity. So now this is loading kind 2. Now it's natural to think that what about bending, which is our loading kind 3 or type 3. It's better to use type, which is basically bending is a different. So we have so far we have the axial load or linear deformation, this one. This is linear deformation. This is angular deformation, torsion. And now what about bending? Bending is a completely different animal. So if you have, let's say this is your beam that is fixed, for example, from one side to the wall, the moment you apply a load here, right, this is going to go down. I want to draw it with different colors. So this is going to go down like that, and immediately we realize that you have some sort of deformation here, right? So the deformation here is right here. I can show it. Vertical deformation, let's call it V, from the neutral axis V. And this deformation, it depends in the location of X. Let's take a location X from the left. So V, in fact, the deformation in the case of bending is kind of more complicated than deformation in the linear deformation, this one, kind 1, or the torsional deformation, kind 2. So type 3 or kind 3 deformation, which is bending deformation, is a function of X. So I say V of X. You see that? So now our objective is to finish up all three sort of deformation equation. So we will be able to solve a wide range of problems that they have axial load, torsion, and bending. And they are specifically indeterminate. because the sole purpose of doing deformation analysis is to get additional equation that we can add up to the basic equilibrium equation to be able to solve indeterminate problem. Example, let's say you have a beam that is simply fixed to the wall and you have a load 2K, right? And somebody asks you, say, find the reaction in the wall. Like, for example, you want to design a fixture here, a bolt or something that you can fix it to the wall. You can immediately say, well, this is very simple. If I draw a FVD, that's going to be something like, so you have Fy, force in the y direction, a moment here in the wall, and then you have a 2K here. That's my FVD. So, and I know, well, let's say we have also a AX here. So how many unknowns do I have? 3. 1, 2, 3. How many equations do I have? 3. Because it's a two-dimensional case, and I have 3 equations. So you have 3 unknowns, 1, 2, 3, and 3 equations. Therefore, you are able to immediately solve it, as we did in vector statics. But now, let's say you have this kind of design. This is a wall, this is a wall, and you have a 2K force here, not at the very center. It's somehow slided to the right, shifted to the right. So let's say this is 1 meter from the right, and from here to the left is 3 meters. And this is wall A, wall B fixed. So this beam is fixing both A and B. It's welded to the wall. Now somebody comes and asks you and say, find the support reaction. We want to design a kind of fixing mechanism that keeps it to the wall. Now you have to first find the support reactions, right? So how do you answer him? Well, you first look at him like this, because you first think that, well, this is maybe statically determinate. This is simple. I just simply say, well, if I have 2K here, then I probably have 1K here, right? And 1K here. And there is no moment in the wall, right? The moment you say that, then your face become like this, because you realize something is wrong. And what is that thing? What is that thing is missing here? Well, let's do FVD. If I do FVD, let's use a different color. I put my borders here around this system, so that's my system. I put borders around it, and then I draw FVD. So what you get, well, that's just too thick. Yes, here, hopefully, yep. Then what I get, I said this is my system, right? I walk around the border. Here you have AY, MA, right? 2 unknowns at A, because it's fixed to the wall. Although you have also in the X direction, but because we don't consider X here, we just don't write it here. So 2 unknowns here. Then you have a 2K noun, which is here, and then you have MB unknowns and BY, right? So the question here is, how many unknowns do you have? Well, let's just simply add this AX and also BX here to make sure that we have everything included in FVD, right? Now, the reason that you get from the smiley face to the unhappy face is the moment you start counting the number of unknowns and number of equations. Well, in this case, I have one system that is equal to 3 equations. But how many unknowns do I have? I have 1, 2, 3 here on the left, and 3 on the right. So 6 unknowns. And this is pretty scary because you need add 3 more equations. All I'm saying right now is motivation to study the deflection coming from the bending. That we really need to know this knowledge. We really need to have this knowledge. Otherwise, we won't be able to solve problems like this, which are extremely practical. Now, I'm trying to add 3 more equations. And what are those 3 more equations? Well, you have one of those equations coming from the deflection, right? You already had it, you already studied that, and I don't know this why. Okay, you already studied that, and you know that the axial deflection of point B with respect to A is equal to 0, right? That means that when you apply any kind of loading here, this point B on the wall is not going to move with respect to A because both of them are fixed wall. You already had this before. So this is going to give me one additional equation. So total number of equations is so far 4. Now the question is, how can I get 2 more? Now this is the question. In fact, this is a motivation to start learning deflection analysis coming from the bending. Well, let me just look at this picture here. Let me zoom on it. Hopefully I will be able to zoom on it. No, I don't think I can zoom on it. Yeah, I should have used another software to do that. In a regular notes, I don't think I can zoom on. Anyways, so if I consider this picture, let's call it figure 1. Figure 1. I see that the deflection, the vertical deflection at both point A and B is 0. How come that's possible? Let me draw it here one more time. This is your beam, a little bit bigger. We need to zoom on it. This is the wall, fixed. This is the wall, fixed, right? And this is my 2K force. Now, assume that this 2K is slowly applied and the beam goes under some deflection. Now I want to draw the shape of deflected beam. So I use another color like red, and I have something like that. And in the wall, this point, you see, it's not going to go down or up because it's well to wall. This is fixed. But the moment I come, I detach myself from that, I go a little bit down, right? I go a little bit down, and I go somewhere. It's not necessarily at the middle because this loading is not symmetric. If the 2K force was at exactly the middle, the bottom line of the deflection curve would be exactly in the middle. But I go somewhere and I reach my absolute minimum here, and then I go up, and then I come back to this point A, then I come back to point B. This is the deflected beam, right? This is in fact, this is the neutral axis of the deflected beam, more precisely. So that means that if this is your actual beam, I need another color, green. This is the center. You see, you remember we talked about neutral axis that we pass through the centroid of this beam, right? This is the same thing. It goes like the red line. So the actual beam, so in fact the red one is in fact your original green dashed line, which is your neutral axis. Now, where is the beam itself? Well, all you need to do is to go, probably I need blue, is to go a little bit up like that. This is the top part of the beam. And a little bit bottom like that. This is the bottom part of it. This is a complete animated form of or visualized form of beam deflection. Now, all I said here is to give you the motivation that how can I, let's highlight it, how can I get these two additional equation? This is the main question. How can I get two more equation? Now, what do you see in this last picture that I plot here? What do you see? Just look at it. Well, look at point A. What do you see? Well, if this is vertical deflection, V of x, what is the vertical deflection at point A? Well, the answer is immediately V at x is equal to 0. If you take x from the left, you remember we did this so many times, taking x from left, drawing the either moment diagram, shear diagram, axial load diagram, torsion diagram, torque diagram, anything, right? So here V at x is equal to 0. This is point A. What is that? That is equal to 0. We know it. Even before we formulate the problem, even before we know what the equation is for the deflection. Just from the shape of this, from the physics, this comes from the observation. We know that. There is no way that point on the A can move. This is one more equation by itself. If I expand this equation, I'm going to get additional information that I can add to my basic equilibrium equation, and then I can solve for all the unknown in the original problem. And what was the original problem? Let's highlight it. This problem. What are my unknowns? AX, AY, MA, BY, MB, BX. 6 unknowns. So in fact, what I'm saying, if I expand this equation that I just got, then I get additional equation 1, because this is one equation. One additional equation that is in terms of AX, AY, MA, and BX, BY, MB, right? So far is 5 equation. How many unknowns do I have? 6 equation. Now you can easily, I'm pretty sure you can guess the extra equation that we need to add it to this 5 equation to get the 6 equation, and then 6 equation, 6 unknown. Then you can solve it, right? So what is that extra equation? The extra equation is, as you can see, look at this point, B. I can write V at x is equal to, what is the total length of the beam? Right here. 3 plus 1, 4 is equal to 0. This is point B. Okay? So this is 6 equation which handles 6 unknown. Therefore, we are able to solve this problem, although this is statically indeterminate. Now the question is, the only thing that I need to be able to solve this, and as engineers get some numbers and report to my boss, is to understand how this deflection works, right? This equation. If I know V in terms of x, then I can just simply expand it, substitute here, expand it, and then I get my extra equation, and then I solve it. Now that's what I want to discuss today. How can I find the deflection equation? Let's write it here. So the result of this discussion is, how can I find the deflection equation? Again, why do I need the equation? Because I need to expand this equation and add it to the basic equilibrium equation to get a statically indeterminate problem converted to a determinate problem, and then I can solve it and get some bunch of number, and then as an engineer my job is done. The rest is the other teammate, right? So here, in order to be able to study that, I need to make more drawing, lots of drawings here. So let's go back to the problem that we solved before. We had the problem that if I have a beam that goes through some deflection. You may remember this curve from many lectures ago. And if I had some kind of loading here, like moment, force, whatever, and if you consider a section of here, say this is radius of curvature, this is center of curvature, and this is let's say this is neutral axis. Let's get another color here that passes through the centroid. Look, this is not necessarily the half of it, it's the centroid. Now if the cross section is perfectly a square like that or circle, yes, its centroid is half. But if your cross section is like a kind of a profile, then your centroid instead of half goes down, as you can see. You know that, right? So I just draw a red line here just to show the centroid typically, which is usually in the middle, but it's not generally correct in this case. You got to be careful about that, because that's going to change your result very, very rapidly. It's very sensitive. Anyway, so let's go back to this problem of cutting. So I'm considering, let's use green color. The centroid, put the center of the curvature. This is something else. It's not the centroid. The centroid is right here. You see the centroid of cross section. They also call it the geometric center. So it has different names. But the center of curvature is the center that this curve for the neutral axis that I'm actually drawing in red right here, this is going to deflect toward it, the center of curvature. Just like we had in calculus, we had a curve that when the ball or convexity is upward, the radius of curvature goes up. When the convexity is down, the radius of curvature goes down. So we can also study this center of curvature, and let's say from here to here is the radius of curvature rho, and also let's consider a point here located from a distance y with respect to the neutral axis, and let's also consider a point on it. And also, in addition to that, let's say this point also is x from the left at location x. Now I'm considering this little slice here. Now let's just slice it right here, d theta, and from here to here let's call it dx. Now I want to zoom on that little plot that I made, right? So if I zoom it right here, I want to exaggerate. So this is the top of the beam, and then this is also, probably I need to use a red color. This was my neutral axis, which I originally drew it in red. Let's write it here. How do you write neutral? Neutral with EU axis. Hopefully that's right. Then I use a point here. Then I use black, which is located y from, so that's your kind of element, from the neutral axis. And from here to here, this is your center of curvature. Center. I'm just zooming this part of the plot here, bigger part. This half the way beam, right? Center of the curvature. All right. So, and also from here to here is rho. So rho y and everything I need. Also, you know that if the beam is not deformed, as we discussed it before, let's put it in the left, undeformed shape of the beam, I draw it on the left. Look at it. This is an undeformed shape of the beam that before we apply the moment M and force F. So if I consider the undeformed shape of the beam, this is my neutral axis. And I know that from here to here, I have minimum number of deformation. Why? Because the stress in the neutral axis is 0. So in fact, if this is dx, this is also dx. It doesn't change the length because the stress is 0 there. There is nothing that can change the length. The stress is 0. What about at location y, located from the neutral axis, right here? Well, originally, if I consider that length as ds, originally that ds is equal to dx. Look at this square right here, undeformed. This is undeformed, right? But when I apply loading on it and it bends upward, then I see this ds is no longer ds. This is ds prime, which is smaller than ds. Why? Because on top of the beam you have compression, as you can see from the figure, so the length decreases, right? But again, dx remains dx in both undeformed, and this is deformed version, right? So what can I say about that? Well, we already have done this, but very quickly in many lectures ago. The video is available, but I just wanted right now to focus on this part better, because we will end up with some differential equations, so we should fully understand this part. So now I go back to a strain analysis for this simple deformed part. I say, well, the strain, look at this point right here. The point here, I want to find the normal strain is change in length, definition of normal strain divided by original length. The first thing we discussed in this class, which was equal to delta over L0. Now in this case, what is the change in the length? Well, the change in the length is equal to excuse me, ds prime, or if you put it, take a positive, write it like this, ds minus ds prime. The change between the original length excuse me, which I just highlighted here, this is dx, original length, subtracted by excuse me, the change excuse me, the change in the the change in the deforming, which is ds prime. So that's my delta, divided by initial length. The initial length is simply ds, which was equal to dx. So here, this equation can be easily written as the exact equation, dx minus ds prime divided by dx, because ds was nothing except the dx. Look at here, dx. If the if this is x from the left, that's gonna, that little part that we caught is dx, right? So you can write, instead of ds, we can write dx minus ds prime divided by dx. Okay, so now I'll go to this general arc right here. What can we write for dx? From that arc, I can write dx is equal to rho, which is a radius curvature, which is from here to the top, times this angle. And what is that angle? that angle was, look at here, d theta. So rho d theta is my dx. Look at this equation. What about ds prime right here? What about the length of this arc? ds prime is equal to from here to here, whatever it is. So what is that? That is equal to rho minus y. If y is from here to here, then that's entire rho minus y times d theta. This is my other equation. Now let's substitute equation 1. Let's call this 1, 2, and this is 3. Let's substitute equation 1 and 2 into equation 3. So I get my normal strain. I wish this could go down. Yeah, my normal strain, I know that it's negative, but I just write it in the positive form. Why is negative? Because the length decreases, right? But I just write it in positive to get just the magnitude of it. So epsilon normal is, I just plug dx from equation 2 and ds prime from equation 1. So I say epsilon normal is equal to rho d theta minus, instead of ds prime, I write rho minus y d theta divided by dx, which is simply rho d theta. Now let's simplify the top. The top becomes rho d theta minus rho d theta plus y d theta divided by rho d theta. Okay, so this rho d theta cancel with this rho d theta. You will end up with y d theta divided by rho d theta. Whatever d theta is, they cancel out. You get y over rho. That's what you get. So your normal strain, or epsilon, let's write it here. Epsilon is equal to y over rho. The one equation. But what was epsilon? Go back to Hooke's law. Sigma is equal to E epsilon. This was valid in the normal. Look, this is normal strain, and this normal stress, the Young module of elasticity, this is not shear module, right? It's Young module of elasticity. It's almost twice the shear module of elasticity times epsilon. And what is that epsilon? That's the same thing, epsilon normal. Sometimes I write it like this, but that's just simply epsilon normal, right? So let's plug it right here. So I get, so if you put this equation right here, you get sigma is equal to E times epsilon normal, which is y over rho. So far, we ended up with this equation. But also, if I go back to my lecture videos on YouTube or your notes, to the very early classes when we drive the deflection formula, we found sigma is equal to m over I times y. And what was that? That was the normal stress generated by bending at any location that is deviated the amount of y from the neutral axis. Let's draw it here. Now you remember that. Let's say this is your beam cross section, and then you have some sort of bending that causes this to go up or down, right? And then you have a location. Let's say this is the neutral axis right here. A location, let's say right here, y. This is plus, right? Y plus. That is located from the central, the neutral axis. Here we had the normal stress generated there, sigma, was equal to the magnitude. Of course, you remember there was a negative sign here, that if you note that if you write this epsilon as also negative, because I wrote it positive here, right? Just magnitude. This cancel out with this, and again you get the same formula I'm going to get right now. So basically it's all about talking negative sign that will cancel anyway. So let me clean up these things here, and I write this formula. So I had this formula long time ago. This normal stress at any point at y is equal to the moment, and what was the moment? The moment in that cross section divided by I. And what was I? I was, if you take this axis xx that passed through the centroid and is the symmetry axis of that cross section, is going to be ixx times y, and y is measured from the centroid. That's the reason the first step is to find the centroid. So now I want to do my final step by derivation by combining these two equations. So let's call this equation number 4, right? Let's say this is equation number 4. Let's say this is 5, and this is 6. So by combining equation 5 and 6, you can simply realize that, well, because sigma is equal to Ey over rho from equation 5, and from equation 6 sigma is equal to m over Ixx times y, then they should be equal, right? Because it's sigma, the left hand side is same. So you simply say the right hand side also should be same. That means that Ey over rho should be equal to mi over times y, right? Now this y simply cancel with this y, as you can see, and then you will end up to this important equation. 1 over rho, which is the radius of curvature, is equal to m over Ei. Let's call this equation 7. What a nice number. 1 over rho is equal to m over Ei at any x. Well, you know that m could be, when we say m, we don't talk about a constant. It could be a function of x. Also, the moment of inertia could be also a function of x for something like a tapered beam. E could be a function of x for a composite material. So don't forget that. And also the radius of curvature is function of x, right? So just for simplicity, I just write 1 over rho is equal to m over Ei. But every single of these, in fact, is a function of x. Now we want to go back to the calculus, a little bit trip to the calculus, when we had a function like that, and for every point on this curve, you had, it's right here, for example, here, you had the definition of center of curvature and radius of curvature, rho of x. Let's say this axis x, and this is function v. So the radius curvature was like that. Now the moment you come a little bit forward, you increase x. Now here your center of curvature goes down because the convexity is down right here. Rho of x plus delta x, and now your center of curvature is down. Now if you go here, for example, you get a different radius of curvature with a different center of curvature. Now we don't want to do calculus again, because we assume that this is a prerequisite. So I just use a result, the end result of equations we derived in calculus. Now if I want to do that, all I need to do is to just go to Wikipedia and just Google it and see what equation I get, right? So if I go to Wikipedia, let's do that, and I type radius of curvature. Let's say you forgot your calculus book, or you just return it because you borrow it, or you just gave it to your friend, whatever. Wikipedia is always your friend. Now all you need to do is to go to one of these articles in the Wikipedia, and now for general function you can find like f of x right here. Do I have a cursor that I show it? Right here, I can zoom on it. You see this equation, rho t is equal to 1 plus f prime square t to the 3 over 2 divided by the second derivative at t. I just simply use that. In my nomenclature, this equation becomes rho, let's just switch back here, rho at x, because t there, the time here in my application is x, the location across the beam. It's just a change of variable. The mathematics is the same. Is equal to 1 plus the derivative rho prime x to 3 over 2. Let's go back. I forgot the formula. No, to the second power, the entire thing to the 3 over 2 power. So the first derivative to the second power, the entire thing 3 over 2, and this absolute value right here, divided by the second derivative of rho, sorry, this is f, this is not rho, look at here, this is f. What was f in our application? F is v, the vertical. That's exactly what we want to find to solve indeterminate problem, right? So f here in the calculus is general, right? It could be anything. In our specific course, this f is v, or vertical deflection, the thing that we want to find. So instead of f prime, I put here rho prime, I just write v prime. So v, this first derivative prime. Now here, by the same token, becomes v second derivative at x, right? This is the exact translation of the same formula we have from Wikipedia. So let's go back, compare. Rho of t becomes rho of x, because t, we don't have time. Here we have x. And then 1 plus f prime squared becomes 1 plus v prime squared, the entire thing to 3 over 2 divided by second derivative with respect to x, right? That's exactly the same formula I have here. So I want to make the final observation here. The thing that I have, my deflection, let's say in my application, I have something called a small deformation. This is an assumption, is always valid in engineering, specifically in our course, that everything is linear, a small deformation, not large deformation, not plasticity. So that means if you apply a load here, like 10K, we draw something like that, like exaggeration, that this goes down such a big amount, V. But in fact, this V is 1 micrometer. It's so tiny that we don't even see it. I've talked about it several times. What does it mean is dV over dx is 0 in our application. That means the slope of this curve, look at this, the slope of this curve is the slope of this line, right? Theta. This is so small that the change dV dx or V prime is almost 0, right? Because the theta is small, right? So what I can do here, let's go back to this equation. I can approximate this equation with V prime is small, not exact 0. Look, small. And when you have a value that is small and you raise it to power 2, what do you get? You get very, very small value. So what I can do, I can just say, well, this thing approaches to 0 in my application. So if I have 1 plus 0 to the 3 over 2 power, is the entire thing is almost 1, right? This is called engineering approximation, because we don't want to solve the complicated problem coming from nonlinear term here that I just circled it. V prime square, right? So my approximation right here becomes, which is a very, very good approximation, becomes rho of x, the radius at any point, radius of curvature at any point is equal to 1 over v second derivative at x, because the top is almost 1, right? Now let's do the very final thing, this equation 8. So many equations I derive. Now finally we reach to the beautiful part. Let's substitute 8 in 7. What do I get? I get 1 over rho of x, which is rho of x according to 8 is 1 over the second derivative of v of x. Now if you put it there and bring it to top, you get the second derivative of v of x is equal to m at any x divided by e at any x times I at any x in general. That means the second derivative of deflection is equal to moment times shear module of Young module times cross-sectional moment of inertia measured with respect to the centroid. It's very important, measured with respect to the centroid. Now usually this equation, because you have x everywhere, they simplify it. They write the second derivative is equal to m over ei. This makes the equation to be compact, right? The notation is simplified. Now this is the final thing I need to compute my deflection. Now you may ask the question, how can you compute your deflection using this equation? Well, what is this equation? This equation says the second derivative of v is equal to m over ei. In mathematics, more beautiful notation, you can write the second derivative of v with respect to x is equal to m over ei. And this could be a function of x. Now you want to solve this equation for v, right? What is this? What is this equation called? This is called ordinary differential equation. I strongly recommend you guys take this course if you haven't. Usually in some school they take this as a prerequisite for this course, but I just help you with that. I don't want you to have the preliminaries for this because I just teach you how to do that, right? So this course, which they take the first initial ODE by itself is a course, undergraduate course, that they teach you how to solve this sort of equation, right? Now you can say, well, if you have, how do you solve this equation? The second derivative, for example, of deflection with respect to x is equal to sine x. For example, how do you solve that? Well, you say, well, I take one integral from both sides, right? The very easy way. So you get dv dx is equal to, what is the integral of sine x? Is negative cosine x. Why? Because if you take the derivative of negative cosine x, it becomes negative sine x, right? Plus c1. This, what is this? This is simply taking integral from both sides. You see, you get one constant of integration. You had this in calculus. Now take another integral. What do you get if you take second integral? This equation. You take one more integral, so you get v at any x. Look, you already solved for v is equal to negative sine x. You already have a negative, and you take the integral of cosine, which is sine, right? Because if you take the derivative of it, just take this negative here. If you take the derivative of sine, it simply becomes cosine, right? Plus integral of c1 is c1 x plus another constant of integration, c2. There you go. What did I do? Well, I just solved for deflection for sample given m over eix, which was sine, right? So these equations are not hard to solve. All you need to do is to use double integration. That's the reason in a structural analysis this method is called method of double integration, to find the deflection from the bending moment. There are other methods, Castigliano's theorem, energy method, moment area method, conjugate beam, things like that. There are a lot of methods that we teach in structural analysis to make this easier. But the very fundamental one is the double integration method, that you basically solve ordinary differential equation. This is more like math method. It is very robust, but sometimes it takes a while, right? So just go back. The most important equation I drive in this lecture today is, let's highlight it, is this guy right here. This equation. Sometimes I had a student memorizing this, which is, I think this is a good investment to memorize because this is extremely important equation. But in the test, I will give it in appendix, so you don't really need to memorize it. Example. So I want to use that equation to find deflection. Let's say you have a beam fixed to the wall from the left, and you have a 2K force here, right, on one side. Let's use a finer pen. And now the length of this is just 1 meter, and E times I is 1. Take EI is equal to 1. Now the question is, well, you know that if you have this loading, let's draw the deflected curve. This is going to go down like that. This is a neutral axis, right? It's going to go like that. The question is how much this is going to go down. That's the question. Okay? Now, in order to answer this, well, I can use this equation, right? Let's write here, that equation is equal to second derivative of v with respect to x is equal to m at x divided by EI. And this specific case, my EI is just simply 1. So that simply tells me the second derivative of deflection with respect to x is equal to moment at x. So in order to solve it, you see the previous example, moment was simply sine x. It was given to me, right? In this example, what should I do? Well, I know that you guys know the answer. You have to find moment versus x, or you have to plot the moment diagram, right? So let's do that. So if I want to do that, I make FVD. There you go. I have 2K. Right here, from here to here is 1 meter. Here in the wall, I have two reactions like that. The vertical force is equal to 2K to keep this in equilibrium, and the moment is equal to this, the other direction, and is equal to 2K Newton meter, because this is Newton times meter, 2K Newton meter, to keep this in equilibrium. Well, all I did, I simply wrote the equilibrium equation. So now I really wish I didn't have this keyword. This keyword is very interrupting here. All I do, I just cut it from the distance x from the left and make my FED. So this cutting. So you already have a 2K Newton meter here. You already have a vertical force, which is 2K upward. And from here to here is x. And here you're going to get V of x like we did before, shear force, and M of x. Now summation this point x, summation of moment about point x, 0. That would give you M of x with positive sign. V doesn't have a moment. And then you go plus 2K Newton meter, negative 2K times x is equal to 0. So positive mx plus 2K, negative 2K times x is equal to 0. Then you get m of x is equal to, take everything to the right, 2k times x minus 1. That's what you get for moment. Now plug it here in this equation right here that I'm check marking. Plug it there. So you get the second derivative of v with respect to x is equal to m of x, which is 2k times x minus 1. Take the first integral, both sides. What do you get? You get dv dx is equal to 2k times x minus 1 square over 2 plus c1. If you don't believe it, take the derivative of both sides. If you take the derivative of both sides, this becomes the second derivative of v with respect to x, and this becomes 2k times 2 times, let's write here, 2k times 2 times x minus 1 to the first power times 1, and you already have a 2 here, plus the derivative of c1, which is 0, because that's a constant, right? So you cancel this with that, and then you get back your original equation, which is the second derivative of v with respect to x is equal to 2k x minus 1, right? So in fact, this is correct integral of the first equation. Go ahead and take one more integral of both sides. What do you get? You get v at x is equal to, well, let's simplify this, 2k by 2, so you have 1k here, and then you have x minus 1 to the 3 divided by 3 plus c1 times x plus c2. That's it. That's a deflection curve. Now I ask you, as an engineer, can you find the deflection at x is equal to 1? That's my objective. Can you do that? Put x1 here. What do you get? You get v at x1 is equal to 0 plus c1 times 1 plus c2. Is this a number that you can report? No. So in order to solve this problem, you first need to get c1 and c2, which is basically a constant of integration. How do you get c1 and c2? You remember, if you had the course, the ordinary differential equation, you had something called boundary conditions, right? So if you didn't have that course, I'm telling you here, you need to apply boundary conditions here. So what are the boundary conditions? Let's go back to the beam. Look at the beam right here. The question is, does it move here at this point? Let's call it A. No. So the V at x is equal to 0 is always 0. This is called boundary condition, you see, because it happens in the boundary of system, either here or here. This is called boundary condition mathematically, because it happens in the boundary. Also, what about the slope? Well, the slope, look at here, you see, the slope of the neutral axis with respect to the flat line, the x-axis, this theta, the slope theta at x0 is also 0, only at this point. I'm just talking about only at this point. At other point, as you can see, we gradually get some theta, right? Only at point A. So we have these two conditions. And we know that from the very, very previous lecture, theta, the slope was dv dx. If you don't believe it, prove it using the equation that we had here. You can prove it by using this equation. Let me show it to you. You can prove that by using, where is the curvature equation? You can prove that by using the curvature equation, which is basically right here. right here, and this equation, epsilon is equal to y over rho. You can prove it by combining that. I'll give you as a homework. It's extremely easy to do that. So I have these two conditions. Let's write it here. V at x is equal to 0 theta, which is equal to dv dx, which you can prove it at x0 is equal to 0. I have these two conditions from the physics, from the boundary. They call it boundary conditions. Now, let's apply it to this equation to get two unknowns, C1 and C2. Look, I have two conditions and I have two unknowns, right? 1, 2. Then I can simply get my two unknowns. So if I apply the first theta, let's call this boundary condition 1 and 2. If I apply the second condition, I get theta, which is dv dx, which is equal, just simply take derivative of that. What is dv dx? dv dx is simply 1k, 3 cancel out with 3, you get x minus 1, 2, just take the derivative of this, right? So you get 1k times 3 times x minus 1 to 2, 3 cancel out with bottom, times the derivative of inside, plus c1, okay? And c2 is 0. So this simply theta, or derivative of v with respect to x, which gives you exactly this equation. And c2 is just constant derivative is 0, right? Now evaluate this at location x is equal to 0. According to this boundary condition, this is equal to 0. So put x0, what do you get? You get 1k times negative 1 squared plus c1. This should be 0. So your c1 is equal to negative 1k. Okay? So you already got c1. What about c2? Apply v at x is equal to 0 is equal to 0. Apply this condition, right? So let's go back to original equation. V at x0 is equal to 1 k over 3 negative 1 third plus c1 times 0 plus c2 is equal to 0, right? Then you get c2 is equal to negative 1 k over 3, which you take it to the right, and then it become positive 1k over 3, right? Then you put it here in this equation. You get v of x is equal to 1k over 3 x minus 1 3 plus c1, which is negative 1k times x plus c2 plus 1k over 3. That's the deflection of your equation, right? So what is the deflection at x0? The deflection at x0, put it here. This is at the wall. You put 1k over 3 x0, which is negative 1 to 3, minus 1k times 0 plus 1k over 3. So you get what? Negative 1k over 3 plus 1k over 3, which is 0. That's correct. That's a boundary condition. The deflection at point is x0, 0. What is the derivative of deflection at x0, which is theta at x0? What is that? Well, take the derivative of this equation. You get 3k over 3 x minus 1 to 2 minus 1k, right? Now evaluate that at x is equal to 0. Then you get 1k, so this 3 cancel out with this 3, so you get 1k times negative 1 to 2 plus negative 1k 1k minus 1k is 0. It satisfies your second boundary condition, right? So it satisfies both boundary conditions. So this equation is right. This is my final answer. Now you evaluated deflection at x is equal to 1, the very end of the beam, not x0. x0, look at the picture. x0 is x0. x0 is the wall. x1 is the very end. Put 1 in this equation. x1 is equal to, when you put 1 here, the first term is 0. The second term becomes negative 1k times 1, right? Plus already 1k over 3. So this becomes negative 3k over 3 plus 1k over 3, then become negative 2k over 3. Right? So that's your deflection at point 1. So that's the final answer. Look, it's negative. Why? Look at the picture. Well, it goes down. You see here? It goes down. That's the reason it's negative. Now, I'll give you some examples, some practice problems, some homeworks. In addition to the torsion, I haven't posted the torsion exercises. So we're going to have some simple torsion problem, indeterminate torsion problem, and then I put some basic just solving basic equation of beam deflection. Now this is the first part of beam deflection. The second part I'm going to solve more advanced problem, and in the third part I'm going to solve the actual problem that I started this lecture with it, which is indeterminate problem, the problem like this one, which is very, very practical and engineering. Okay, I think that's enough for today, and I'll see you later.